Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the welding of metals. In this particular section, we will try to talk about the way by which the metals and its properties affect the ease of welding, or you can say the weld joint properties. Okay. So, as far as the content is concerned, in this presentation, we will try to talk about the way by which metal properties affect the fusion welding. Say these metal properties are the mechanical properties. So, mechanical properties like yield strength and the percentage elongation. Okay, percentage elongation. These are the two important characteristics which affect the ease of welding with regard to the residual stresses and distortion tendency. Okay, then the chemical properties, which is particularly composition. No, so composition affects the like affinity with the gases, leading to the inclusions and porosity formation, inclusions and porosity formation. Then it also affects the oxide and nitride formation tendency, and if there is a chemical heterogeneity, then it will result in significant metallurgical heterogeneity and change heterogeneity in terms of the mechanical properties. Then the material properties, say physical properties, if we see of the metals, then the melting point, okay, melting temperature, melting point temperature of the metal, one thermal expansion coefficient, another, and solidification temperature range is the third. These are the three very important properties with regard to the fusion welding that affect the ease of welding. If the temperature is low, it will be easier to melt and develop the joint. If the thermal expansion coefficient is high, then it will cause greater thermal expansion and contraction, leading to the increased development of residual stresses and distortion tendency. Then solidification temperature range. Okay, wider solidification temperature range means increased solidification cracking tendency. Okay, due to the increase, especially under the conditions when there is high tensile residual stresses or the welding is being done under the restraint condition. Then as far as the dimensional properties are concerned, especially it is about the thickness. Okay, so thickness certainly affects the welding, because it affects the choice of the welding process. If it is very thin, maybe we can work with the TIG, or very thin means it is less than 1 mm. Okay, then the TIG or the laser can be used. But if it is moderate range, like say 1 to 5 or 10 mm, then any welding process can be used effectively. But if it is very thick like 50 or 100, then again it will make the job of welding difficult. So, thickness affects the not just the ease of welding, but also the choice of the welding process and the development of the weld joint as per the desired geometry, accuracy, free from the residual stresses and distortion. Then another very important aspect related to the metal is the metal strengthening mechanisms. Metal can be strengthened by the different mechanisms like work hardening, grain refinement, solid solution strengthening, then precipitation hardening, then dispersion hardening, transformation hardening. So, there are various mechanisms, and depending upon the way by which the metal has been, a given metal has been strengthened, the effect of the heat being used during the welding, that will be affecting the weld joint and the joint properties in different ways. So, we will try to see how the metal strengthening mechanism will be affecting the joint properties, and so this is the another very important aspect, another important metallurgical aspect. Okay. Then weld thermal cycle. No, during the fusion welding, certainly the heat is used, whether it is gas welding, arc welding, laser welding, or electron beam welding, or any other heat source which is being used to realize the fusion of the fairing surfaces. Okay. So, whenever the heat is applied, the zones which are being heated by the suitable heat source, that will be causing not just the melting of the fairing surfaces, but also the regions which are close to the melted zone, the regions adjacent to the melted zone will also be experiencing the rise in temperature, because of the heat will be because heat will be dissipated due to the thermal conductivity of the metal. So the neighboring regions will also be affecting rise in temperature, and therefore, we will be having the heat affected zone. because of increase in temperature the structure and properties are affected. So, we say that this is the heat affected zone. That significantly depends on the kind of the thermal cycle being experienced. Thermal cycle means the temperature and the time relationship being experienced at a particular point. Say these are the plates and here is the heat source which is being passed through the along the weld line, and there is a particular location away from the or in vicinity of the weld zone. So, if we try to see the way by which temperature is changing at location 1 and 2, so that will be affected by, so this variation in temperature as a function of time is known as the weld thermal cycle. It will be going like this, okay, like this. So, this is for point 1 and this is for point 2. So, our heating rate, cooling rate, peak temperature, all three are affected by the location of the point, okay. As we move away from the weld thermal cycle, away from the welded zone, or the heating rate, cooling rate and the peak temperature all are reduced, okay. So, these thermal cycles, this variation in temperature as a function of time, which is known as weld thermal cycle, is affected by the heat input. This is one, preheating temperature which is being used, if at all being used during the welding, physical properties like thermal conductivity and section thicknesses. So, there are multiple parameters related with the welding as well as the metal which is being welded, that will be affecting the weld thermal cycle being experienced for given condition. So, heat input, preheating, physical properties like thermal conductivity and section thickness. Then the heat affected zone, as I said, during the welding, when we apply heat for the welding purpose, the areas close to the weld joint are affected by the heat in terms of the microstructure and mechanical properties, okay. And that zone which is affected by the heat is known as the heat affected zone, and that depends on the type of the metal, like what is the mechanism which has been used for strengthening the metal, that actually significantly determines the width of the heat affected zone. So, whether it is work hardened, dispersion hardened, precipitation hardened, transformation hardened, or grain refined, or you can say precipitation hardened, transformation hardened, grain refined, dispersion hardened, work hardened, or any other mechanism which has been used. So, the mechanism being used for developing a metal, that affects the width of the heat affected zone significantly under the given welding conditions, okay. And how it is affected, about that we will be talking. So, the characteristics of the weld joint, how these are affected when we apply the heat for fusion welding in case of the transformation hardening metal, work hardening metals and precipitation hardening metals, because there are certain metals strengthened by certain mechanisms are affected much more by the heat being applied for the welding purpose as compared to the other metals is strengthened by the other mechanisms. Other mechanisms, say solid solution is strengthened as well as the dispersion hardened metals are less affected by the heat of the welding as compared to that of the grain refined, precipitation hardened and transformation hardened and work hardened. If the metals are strengthened by these mechanisms, then the effect of heat will be much more as compared to these two mechanisms, solid solution strengthening and dispersion hardening. So, we will be trying to see that how these the metals strengthened by the different mechanisms are affected by the application of the heat, okay. So, as I said, the metal properties and the welding, especially the fusion welding, the mechanical properties affect the residual stresses, because the distortion tendency as well as the cracking tendency also. Say if the higher is the yield strength, then higher will be the residual stresses that will be left in the weld joint. Say this is the weld joint which is being developed, and if you try to see the residual stress distribution across the weld, it will be like this. So, in the weld zone, the residual stress is tensile and in vicinity it is compressive, okay. This is one. So, what will be the maximum residual stress that will be developed at the weld center line? That will depend upon the strength of the material, especially in case of the autogeneous welding. But if we use the filler metal of the lower yield strength, then this residual stress distribution can be like this also, where the maximum stress being developed in the weld joint at the weld center, that will be minimized or reduced. So, reduction in residual stress will reduce its adverse effect on the weld joint performance. Okay. Another aspect is like if the metal is having the lower percentage elongation, then it will show greater cracking tendency. That is the another aspect. So, not just the yield strength is important, but also the lower elongation, lower ductility will enhance the cracking tendency, because in any case the residual stresses of the tensile type will be developed during the fusion welding of the metals. Another aspect is the dimensional characteristics like thickness. Okay. So, if we are working with the very thin sheets like 100 micrometer thickness, 500 micrometer thickness, then we will see that the control over the heat application must be good enough. Otherwise, what will happen? There will be melt through kind of thing. There will be quick melting and the molten metal will start flowing here and there, and we will be experiencing the problem of the melt through. Okay. And if the thickness is moderate, like it is like 1 to 5 or 10, then probably the melt through issue is not that serious. Okay. But so, what we have to do? We have to control the heat in such a way that the melt through problem is avoided, while at the same time through thickness penetration is also realized. Okay. But when we are handling with the greater thicknesses, okay, then it is important that for a given heat source we are able to realize the through thickness penetration for development of the sound weld joint. If it does not happen, then what will happen? Our the thickness, if the penetration is partial, then there will be a some zone, weld zone, that will be left unwelded, and this will be reducing the load resisting cross sectional area, increasing the stress concentration, and thereby it will be reducing the load carrying capacity of the metal. Okay. Then the affinity chemical properties, as far as chemical properties is concerned, many metals are very sensitive to the atmospheric gases like aluminum, titanium, chromium. So, these react with the atmospheric gases very easily, and they form their oxides and nitrides, leading to the presence of their presence in form of inclusions as a weld defect. But on the other hand, there is a possibility that the gases which are present, if the gases are there, they will show the if they are showing the great difference in the solubility of the gases in the molten metal and in the solid state differently. Say in the solid state, the solubility of the gases is very less as compared to that of the in liquid state. So, if the difference between the solubility of gases in the liquid and solid state is much more, then during the welding in the molten metal, the gases will get dissolved easily. Later on, when the solidification will be taking place, these gases will tend to escape out. But this escaping out possibility will be very limited, because the weld metal solidifies very quickly. Therefore, the gases will get interwrapped and resulting in the porosity. Okay. So, if the difference in solubility is very less, then the problem related with the porosity, the gas entrapment tendency will be minimized. Okay. Then we have the chemical compatibility. If the chemical compatibility is not there, then it will be leading to the formation of the undesirable compounds which are very hard and brittle. It will promote the corrosion tendency of the weld joints. So, it is important that the either filler metal is selected in such a way, or the fusion welding of the two metals is done in such a way that they are compatible chemically also. Otherwise, you have to choose a suitable filler metal in such a way that when the two components which are not compatible with each other, so we use the filler metal C, which is compatible with both and does not create much problem related with the embrittlement or the corrosion tendency. Okay. Then we have physical properties. So, thermal expansion coefficient, we want that thermal expansion coefficient is less, but since the material properties, if it is very high, then it will be creating the problem of residual stresses and distortion tendency. If the melting temperature is high, then it will create difficulty in melting, and that will make the fusion welding difficult. And if the solidification temperature range is wide, okay, wider solidification temperature range will promote the cracking tendency, especially solidification cracking as well as the liquefaction cracking. Both type of cracking tendencies are enhanced if the solidification temperature range of the metal is wide. Now, we will try to see that there are different metal strengthening mechanisms and they affect they affect the joint characteristics. If the that metals are strengthened by the different mechanisms, say work hardening, precipitation hardening, grain refinement and transformation hardening. So, these highlighted ones, what it indicates that these are affected much more by the application of heat as compared to the metals strengthened by the dispersion hardening and solid solution strengthening. Why? Because when a metal is strengthened by work hardening means increased number of dislocations will be produced. Okay. These dislocations under the effect of the heat they get annihilated due to the recovery and recrystallization. So, the metals get weakened significantly. The same thing happens in case of precipitation hardening. Lot of fine precipitates are produced in the metal. When the heat is applied for the welding purpose, these precipitates tend to get dissolved, okay, leading to the reversion, means absence of the precipitates or precipitate free zone formation, and that in turn will be leading to the reduced performance of the zones where this kind of reversion or dissolution of the precipitate is happening. In case of the transformation hardening like in steels, no, they are affected significantly by the heat being used for the welding purpose, and most of the time this is the hardening and the embrittlement that will be happening in the weld zone and in the heat affected zone due to the transformation hardening. About that we will be talking little more in the later stages. Similarly, when grain refinement is the mechanism which is being used for strengthening the metal, then due to the application of the heat, mostly the coarsening of the grain coarsening happens, especially in the heat affected zone, because in the weld metal zone properties we can design as per our need by choosing the suitable filler metal, but in case of the heat affected zone mostly the grain coarsening takes place, and the coarsened grain will be leading to the reduced hardness, reduced strength, and that in turn will be reducing the joint performance. Since dispersion hardening is based on the principle of reinforcing the hard particles or suitable constituents, the same is true in case of the solid solution strengthening, where alloying elements are added in the metal, and these are in when the metals are strengthened by just these two mechanisms, the not the neither the dispersed particles nor the alloying elements, these are not much affected by the application of the heat. So, when the fusion welding is done of these two types of the metals strengthened by dispersion hardening or by solid solution strengthening, they are not much affected by the application of the heat. But we know that if we take any metal, okay, like say it is in form of the rolled sheet, okay, and say strengthened by either precipitation hardening or transformation hardening depending upon the kind of metal. Say if it is aluminum, say strengthened by precipitation hardening, and if it is a steel, say it is strengthened by the transformation hardening. But when it is rolled, it will be having the effect of the work hardening also, and depending upon the thermal conditions imposed, it will have the fine grain or it will have coarse grains, okay, depending upon the kind of thermal cycle imposed during the manufacturing. The point here is, it is possible that a metal performance will be dictated by the multiple factors, like due to the rolling it is having the work hardening effect, and due to the presence of precipitates as per the design it will have the precipitation hardening effect, and since it has been say work hardened, so sorry, it has been say it is possible that the grains have been refined, so the grain refinement effect. But when we apply heat, so it is possible like precipitates will get dissolved. Say in this particular case there are fine precipitates coupled with the dislocations, okay, of the fine grain size. So all these things will be compromised when the heat is applied during the welding. Say in the weld zone everything will get dissolved and we will be getting the cast structure, okay. But in the heat affected zone what will be happening, work hardening effect will be lost due to the recovery, precipitates will be lost due to the reversion, okay, and the grains will get coarsened. So, what we will be seeing that the base metal hardness is high, but the HAZ hardness is weak significantly, okay, because the weld hardness will depend upon the kind of filler metal which is being used. So, we will be seeing significant softening of the heat affected zone. The point that here I am trying to make is like if the metal is strengthened by work hardened, grain refinement, transformation hardening or precipitation hardening. Okay. So, a given metal can have the effect of the multiple mechanisms. It is possible like one mechanism may compromise, like in fusion welding of the steel, it is possible that we may be getting the transformation hardening effect in the weld and in the heat affected zone, but at the same time work hardening effect may be neutralized if it was having it if it has been rolled out. Okay. But which effect is dominating, that will ultimately govern and determine the properties of the weld joint and of a particular location. Okay. So, we have to see that in which way the different mechanisms are working in a particular zone due to the application of the heat. It is possible transformation hardening may cause the like embrittlement, while the grain coarsening and the work hardening may lead to the softening. So, in nutshell, how the things are affecting in totality, that has to be seen. So, this is just to elaborate the weld thermal cycle, like say these are the two plates being welded using the suitable heat source, which may be laser or flame, anything. This is the welded section, say, and this is the direction of the welding. If we consider these 2 points A and B, so point A is close to the weld line and point B is little far away from the weld line. And then if we try to study the weld thermal cycle of the location A and location B, then what we will be seeing that the location B weld thermal cycle is showing that weld thermal cycle like this, where heating rate is less, peak temperature is lower and cooling rate is also lower. On the other hand, if we see the location A, for which heating rate is high, means the rate of rise in temperature is high, and then peak temperature is also high and cooling rate is also high. So, these slopes and the peak temperature can be used to determine the various characteristics from the weld thermal cycle. In addition to that, so in addition to these three aspects like heating rate, peak temperature and the cooling rate, what we can also determine how long a particular temperature is maintained at a particular location. Say if we take a particular temperature is of our interest is this, then from by drawing simple this line in the weld thermal cycle curve, we can identify the time for which the particular temperature is maintained, particular temperature or the temperature of a particular location is maintained above a certain temperature. So, we can also try to find out, we can determine the time above which a particular location is heated. Okay. Above a particular temperature, particular location is getting heated. So, this will help in determine the soaking time. Okay. How long particular point is maintained above a particular temperature, that is what also can be determined, okay, using the weld thermal cycle. So, the heat affected zone is then another important part, like say if the metal is this, say this is one metal A, say strengthened by either work hardening or transformation hardening or grain refinement or precipitation hardening. Okay. So, say this is the fusion zone and the zone which is being getting heat because of the thermal conductivity is up to this. So, how do we define if this is the heat affected zone? So, what we have to see is how far the change in characteristics in terms of like loss of dislocation in case of the work hardening metal is taking place. So, that will be indicating the change in properties of the materials. Dislocations will be lost, means this zone will be experiencing the softening like this. Okay. Here the hardness is more and here the softening is increasing because of the increasing temperature. So, the recovery will be more in the locations close to the fusion boundary as compared to those away. Similarly, the grains will be coarsened more, okay, in the vicinity next to the fusion boundary as compared to those away from. Similarly, if we see the precipitation hardening metals, so you say metal is having all these precipitates here, but as we approach towards the fusion boundary, their presence will be minimized, okay, like this. So, here their intensity is more away from the fusion boundary and we approach towards the fusion boundary, their intensity the density is reduced. So, here this is what is happening due to the dissolution of the precipitates because of the high temperature which has been experienced by the zone next to the fusion boundary. So, the distance up to which the change in structure in form of dislocations, in form of the precipitates, in form of the phases, say earlier it was ferrite and perlite, okay. Now after the welding it has formed the martensite. So, wherever these changes are taking place, or they say earlier, or the grain size variation, wherever the up to what distance the these changes are taking place away from the fusion boundary, that will determine the width of the heat affected zone. So, this is one way to look into this, like whatever is the width away from the fusion boundary is experiencing the change, that will be termed as the heat affected zone. That is one way in terms of the metallurgical characteristics. We can also see in terms of the mechanical properties, like the distance up to which there is a variation in the hardness, okay. So, because that will be determining the properties. So, say the base metal hardness is this much. So, we may have the hardness like this, or we may have the hardness like this. So, where both softening can take place or hardening can take place. So, wherever this kind of the variation is taking place due to the application of heat, that will be termed as the HAZ. Okay. So, that is why heat affected zone in fusion welding, it is always there, because heat gets dissipated to the underlying base. Whenever we try to fuse the metal for development of the weld joint, the heat will be dissipated, and this dissipation will depend how far it goes and causes the rise in temperature. That will certainly depend upon the heat and the thermal conductivity and section thickness, etc., many things. Okay. But what up to what extent this heat is causing the rise in temperature, that will be determining the heat width of the heat affected zone. Okay. Now, this width can be very wide or this can be very narrow. Okay. So, means this compromise in properties will always be there, whether it is over a narrow zone or it is wider zone. Okay. So, accordingly we say a wide heat affected zone or narrow heat affected zone. Efforts are always made to reduce this, but it cannot be eliminated because heat will always be dissipating from the fusion boundary to the base metal. Okay. Most of the time HAZ is problematic. Why? Because it causes the change in structure and it causes the change in properties, and because of this we will find the properties are not favorable, either hardening is taking place or softening is taking place, mechanical properties and performance is getting modified, corrosion resistance has been lost, it is getting embrittled and increasing the cracking tendency. So, that is why most of the time most of the pH metals get softened. Okay. So, that will be weakening the joint performance. On the other hand, most of the transformation hardening materials like the steels, cast iron, etc., they will be experiencing the hardening and embrittlement. So, because of the hardening and embrittlement, the loss of toughness, increased hardness and the increased cracking tendency will be there. So, we want to minimize the HAZ as far as possible, so that its adverse effect can be reduced. So, here we can see, say, iron carbon system and the weld thermal cycle, which is how we can relate. Say this is the schematic of the steel, okay. Say steel, carbon steel, plain carbon steel, okay. So, for fusion welding we have to melt. So, whatever the zone is melted, that will be above the melting temperature, say 1540 degrees centigrade in case of the pure iron, but it will say greater than 1400 degrees centigrade. So, this is zone which is greater than 1400 degrees centigrade. So, here considering this composition just for an example, so this is the zone where we have the both delta ferrite and the liquid. So, the zone where we have both delta ferrite and liquid, that will be the partial melting zone. Okay. Then there is a zone where we have just austenite. Okay. So, that will be the coarse heat affected zone. Then there is a intercritical zone where both ferrite and austenites are present, that will be the like fine grained HAZ zone. Then there is a zone which is below the lower critical temperature, but above the recrystallization temperature, that will be the recrystallization zone, and then the base metal. So, formation of the different zones in the steel, say transformation hardening metal, that can be related with the iron carbon diagram itself, because whatever the changes that will be occurring in the steel, that will depend upon the kind of maximum temperature being attained in that particular zone as per the iron carbon diagram, and that will dictate the. So, this is just about the heating effect. Okay, all these zones which has been heated to the too high temperature, like say above the lower critical temperature. Okay, all these zones which has been heated above the lower critical temperature, when they are subjected to the rapid cooling, those zones have formed, say, austenite. So, these zones will be leading to the formation of the martensite, because typically the very high cooling rate is observed during the fusion welding. So, all these zones actually form the martensite in case of the carbon steels. Okay, it may be low carbon martensite or high carbon martensite, depending upon the carbon content which is present in the steel. If a metal has been strengthened by the work hardening. Okay, so if the metal has been strengthened by work hardening, then the metal will have the lot of dislocations. Dislocation density is very high. This is the unaffected zone, but there will be a zone which is very close to the fusion boundary. This is the zone where complete recovery will be taking place, because all dislocations will get annihilated. Then there will be location little away where temperature is somewhat less. Okay, and that is what we can relate, say 0.1, 2, 3, 4, and if we see thermal cycle for 0.1, 2, 3, 4, then our peak temperature is reducing, high temperature retention above a particular temperature is reducing, like say this is the recovery temperature. So, that high temperature, if the if the high temperature retention above the recovery temperature is coming down, then what will happen? The extent of recovery will be reducing. So, longer the time above the recovery temperature, greater will be the recovery that will be happening. So, complete recovery, partial recovery, or even partial melting can also take place in case if the alloy is having the solidification temperature range. So, these are the different zones which are formed. One is next to the fusion boundary, this is the PMZ zone, partial melting zone, where both liquid and solid will be there. Then complete recovery zone, partial recovery zone, and in all these cases, if we try to see the hardest distribution, okay, like this. So, here the unaffected base metal, then the partial recovery, complete recovery, okay, and then partial melting zone. In all these, if we measure the hardness distribution across these points, then what you will see, the base metal will have higher hardness, then hardness will keep on coming down. Okay, and a little higher hardness where if you have partial recovery, further lower hardness if you are having the complete recovery. Okay, and then wherever the partial melting, this zone, then filler metal will decide, further filler metal will decide if the hardness will be like this of the weld zone or it will go like this. So, the properties of the weld zone we can alter by choosing the suitable filler metal, but heat affected zone properties will always be compromised, whether the hardening is taking place or softening is taking place. So, that is what we can see here in case of the precipitation hardening and transformation hardening. If it is precipitation hardening, then what will be happening? Our precipitates will be getting dissolved. So, like say this is the weld zone, then the zone B is where complete reversion is taking place, means complete loss of dislocations is taking, complete loss of precipitate is taking place coupled with the grain growth. Then partial reversion, where partial loss of precipitate is taking place with the little grain growth, or recrystallized zone or unaffected zone. So, what we can see here, the hardness distribution of the metal goes in like this. Okay, and this is attributed to the reversion effect that will be experienced by the parent metal due to the application of the heat. But in case of the transformation hardening metals, that again will depend upon the kind of the metals condition. Say if we take the Q&T steel in quenched and tempered conditions, then due to the heat application of the heat, fusion weld will be showing the hardened transformation hardening. So, hardness will be high in any case, but the zone, heat affected zone, will be showing the softening. Why? Because it was in Q&T conditions, and when we apply heat, it gets over tempered, and over tempering causes the softening. Okay. So, Q&T steels in the heat affected zone get softened, otherwise other steels get hardened. That is what we can see here. Steel in normal annealed or normalized condition, in annealed condition it is showing lower hardness, but HAZ gets hardened because of this multi-state transformation that will be happening in the heat affected zone and also in the weld zone. So, the hardness of the weld as well as the heat affected zone, that will be great. So, this is the HZ, this is the weld, this is the base metal. So, this higher hardness is and the weld hardness is attributed to the transformation hardening that will be taking place in case of the transformation hardening metals like cast iron or the steels, whether it is carbon steel or alloy steel. So, here now I will try to summarize this. In this presentation, basically I have talked about the effect of the metal properties like physical properties, mechanical properties, chemical properties and dimensional properties on the fusion welding particularly, and how the metal strengthening mechanisms of a given metal affect the weld joint characteristics in fusion welding. Thank you for your attention.